Okay, this is the part A of the blood chapter. Blood is a connective tissue. Oops. Sorry. This is the beginning of chapter 18 on blood, part A. Blood is a type of connective tissue with formed elements. Those are the cellular components, and that's what we see here in this picture with the red, the blue, and the pink and orange. It's a fluid, or has a fluid matrix, ground substance. That would be the plasma part. It's housed within the heart and the blood vessels. We have what is called a closed cardiovascular system. So it's not supposed to leak out into other areas. Here we have a picture of a large wound, and you have two large leeches. No, these are not grown out in the back, the pond in the back 40. But yes, we do use leeches with large wounds to increase blood flow to the area. Yes, you have to have or give permission for them to be used. Also, they do use fly larvae or maggots on large wounds where they need to do a lot of debriding, and that means removing dead tissue. It is much gentler with the maggots to consume only dead tissue. Yes, they only consume dead tissue. But rather them than going in with a scalpel and scraping that tissue off. Okay, so the functions of blood: transportation of fluid, respiratory gases, nutrients, hormones, waste products, and heat. All of that is one function: transportation. It's a highway system throughout the body. I think they estimate there's like 60,000 miles if you count up all the blood vessels. Okay. So it's a distribution center. Oops. Distribution pathway. You can dump things in there and they come out. Okay. Carries out various immune activities, which is why this is in the same unit as the lymphatic system: identifying antigens, producing antibodies, distributing antimicrobial compounds, and lots more. So again, some of the same cells, all of the leukocytes, which we'll cover in depth in this chapter, are included in both blood and in the lymphatic system. Aids with fluid, electrolyte, and pH balance. This is a location for all of them. This is storage. This is a resource to pull them out. Transportation, getting them from one place to another. Hemostasis and coagulation. Hemostasis is an overall process where we reduce blood loss. Coagulation is a part of that, but it can happen independently of the rest of hemostasis, which we'll also cover. So, functions of blood, and these are similar to the functions of the cardiovascular system. All right, the components. These are all the formed elements. Formed elements are the cellular components of blood. So we have erythrocytes, which are the most numerous. Okay, so erythrocytes are, oops, Okay, these red, which look like an indentation in the, anyway, those are the most numerous. They're the medium-sized formed elements. Platelets are these teeny tiny little circles. They're a fragment of a cell. And then leukocytes, white blood cells. Erythrocytes are red blood corpuscles. Oops. Okay, most people refer to them as red blood cells. That's a misnomer. It's just because most people are lazy. The erythrocyte does not have a nucleus in circulating blood. Leukocytes, monocytes are the biggest of the leukocytes. Lymphocytes are the second most numerous. Neutrophils are the most numerous. Eosinophils are less numerous, and then the least numerous are the basophils. So 5 different kinds of leukocytes. And again, these are the formed elements. Leukocytes are white blood cells. And you'll need those references when you get to the numbers that you'll have to know for the objective with the normal values. The plasma part, okay, so this is a blood test and a definition. Hematocrit, oh shoot, wait, going back here. You have an objective where you're supposed to put normal values. Erythrocytes are the red blood corpuscles. Leukocytes are the white blood cells. And like I said, most people are lazy and call them red blood cells for the erythrocytes. So in some of them, you're going to have 2 ranges. The ranges are for males and females. Now, for testing purposes, I want you to learn one range. The range should include the largest male to the smallest female number. So you only have one set of numbers. Keep in mind that the males are always going to have larger numbers. The females are going to have smaller numbers. So you've got 2 tables. One table will get you most of that information. It should be the first table in chapter 18. Yes, you're going to have to go to your textbook to find that because I'm not going to give you the numbers. You'll also need those numbers for your lab on blood. Okay, so hematocrit is a type of blood test. It's also a term defined. We define it as the percentage of formed elements in whole blood. You can see how they come up with the hematocrit. They take a sample, they put it in a tube. The tube is placed in a centrifuge. It's spun around really fast. The solid portions settle to the bottom and the liquid plasma settles to the top. So formed elements, heavier, plasma, lighter. Okay, then you use numbers. You're going to measure the length of the whole specimen and just the red part and divide. So with hematocrit, what can we tell? We can tell how much, sorry for the pitter patter of feet, that's the Chewini. He decided to come inside. With the plasma and the formed elements, if we take a look at a sample and you have a small amount of formed elements and a large amount of plasma, that means there's not much material, there's not oxygen being transported, there's not a lot of immune activities going on, there's not a lot of coagulation that can take place. So in a tube, where you have lots of formed elements, so a high hematocrit and less plasma, that tells you something else. You're probably dehydrated, or your bone marrow's gone nuts and is dumping all these formed elements into the blood. Either way, you don't have enough plasma liquids in the body. Now, a correlation between hematocrit and blood pressure, and you'll need this answer or this information to answer part of your lab. So if you have low hematocrit, that's going to cause the blood pressure to increase because it's very thin and it's flowing really, really fast. So low hematocrit, high blood pressure. Or lower, if the hematocrit drops, the blood pressure is going to rise. On the other hand, if we take a look at this specimen, when the hematocrit raises, it's going to lower the blood pressure. It's too thick to move. So it's kind of like trying to move a really thick milkshake or pudding through a straw. It takes a lot of pressure. You don't have that pressure. If you're trying to move iced tea or pop through a straw, it moves real quickly. So you have an inverse relationship between hematocrit and blood pressure. If hematocrit drops, blood pressure goes up. If hematocrit raises, blood pressure goes down. Like I said, you need that to answer a couple of questions on your lab. Okay, so the plasma, 92% water, 8% solutes. So we're going to spend time looking at the solutes. The categories of solutes include plasma proteins. There we go. Plasma proteins. And we'll take a look at that group a little more closely. Nutrients, which would include amino acids, carbohydrates, lipids. The electrolytes, which is why we do chemistry. Sodium, potassium, chloride, calcium, magnesium, bicarbonate ions, and phosphate ions are the big electrolytes. And we will cover those when we get to the chapter 24. Nitrogenous wastes or nitrogen wastes. Yes, you need to know these because you're going to see them again when we get to the urinary chapter. Urea, uric acid, creatine, creatinine, ammonia, and bilirubin. They contain nitrogen, but they're waste products. Hormones, respiratory gases, oxygen, carbon dioxide, and nitrogen. Nitrogen's the most numerous. All right, so you have a table, a bigger table. Should be the second table in your chapter. That is going to be needed to get the normal value for glucose, which is part of your lab. Okay, components of plasma. So the plasma proteins, there are three different groups of plasma proteins. The most numerous are the albumins, 60%. Their function is to contribute to blood pressure, both with viscosity and osmolarity. Viscosity is the thickness of blood. So they, along with hematocrit, create the thickness of blood. Osmolarity deals with the quantities of solutes in blood. The another function is transportation. They will bond to hydrophobic molecules, and they act as buffers. Buffers means that they help with pH balance. Okay. Albumins, you can relate that to eggs. The clear slimy part of an egg that becomes white and opaque when you cook it, that is mostly albumin. Okay, second group, the globulins, account for 36% of the plasma proteins. This is actually subdivided into three groups. So we have alpha globulins, beta globulins, and gamma globulins. The alpha globulins also act as transport molecules, except for prothrombin. It's a specific alpha globulin, which is one of our clotting factors. Beta globulins also act as transport molecules, and they help with immune activities. Gamma globulins all help with immune activities, and most, if not all, antibodies are in the gamma globulin group. The third group are the fibrinogens. Fibrinogens account for 4% of the plasma proteins. They are also a clotting factor. Now, in fibrinogen, you have an ending, OGEN, so it's going to get altered to an active protein. Prothrombin has a prefix that indicates it's an inactive molecule protein that has to be altered before it can do its job. So three kinds of plasma proteins: fibrinogens, globulins, and albumins. Production of blood. Now, this is covered in about 4 areas in your book, and we're gonna cover it all together. So, hemopoiesis is the production of blood cells. We also see it spelled as hematopoiesis. Oops, EISIS. That's the ending of it. Hematopoiesis. Production of blood cells. Hemocytoblasts, also called stem cells. They're also referred to as pluripotent stem cells. They have the potential to become several different functional mature cells. So these are the immature cells that produce the formed elements or blood cells. And so you see a representation here, and it can be matured into any of these, plus a couple more. Move this over here. Hemopoietic tissues, the tissues that are responsible or have potentially make formed elements. Myeloid tissues are the red bone marrow. They produce all kinds of formed elements. Lymphoid tissues in adults only produce lymphocytes. So lymph nodes, the thymus, the spleen, they're going to produce lymphocytes in adults. Now, like we said in the lymphatic chapter, the spleen produces all of the formed elements in the fetus. And then as the infant grows and gets more bone mass, more bone marrow, that takes over the job. Okay, the process of hemopoiesis. Step one, stem cells are going to replicate in the myeloid and lymphoid tissues. So this cell is going to replicate over and over and over and over. Second step, the stem cells are chemically induced to become what I learned as committed cells, and now they're referring to them as colony forming units. Again, these aren't all of them, those are most of them. It doesn't show the progression of platelet development. So first two steps. The third step, the committed cells are chemically induced to become precursor cells, and that's this yellow column. Once a stem cell becomes a committed cell or colony forming unit, it can't go back to being a stem cell. Once it becomes a precursor cell, it can't go back to being a committed cell. So chemically induced, there are certain chemicals that are exuded by the bone marrow and the lymphatic tissue that causes this maturing process. The last step involves the precursor cells becoming specific formed elements, and that's what we see listed in the blue column. So, pretty straightforward, except down here for lymphocytes. And we've already mentioned this with regard to the lymphatic system. The lymphocytes require more specialized chemicals to get them to become specific B cells, T cells, natural killer cells. So again, chemical inducement, but there's a little bit more. Now, you don't have to know these numbers, but I do want to expose you to them. So adults produce about 400 billion platelets, 200 billion erythrocytes, and 10 billion leukocytes every day. So your bone marrow and your lymph tissue is really, really, really busy. Okay. Erythrocytes. Erythrocytes are the red blood corpuscles. Again, most people are lazy and refer to them as red blood cells. They're a flexible biconcave disc which lack a nucleus in circulating blood. 2/3 of their volume is filled with hemoglobin. About 280 million hemoglobin molecules per erythrocyte. They last about 120 days. So biconcave, oops, that's this curve and this curve. I think they look like a Smartie candy. You can also see it here and here. So when the nucleus gets reabsorbed and broken down prior to entering the bloodstream, it causes the middle of the cell to collapse. So basically, erythrocytes are a suitcase for hemoglobin. Flexible, they can bend as they go through capillaries that get real small. The function of erythrocytes is to transport hemoglobin, which is going to bond to both oxygen and carbon dioxide. So here we see, erythrocytes all lined up, passing through capillaries. Hypoxia is what's going to cause the production of erythrocytes. So the first thing that your body does when it's low on oxygen is to make more erythrocytes and hemoglobin. The first thing, not the second thing, not the last thing. So we make erythrocytes and hemoglobin in order to respond to low oxygen levels in the body. So here we have a representation of hemoglobin. This is the structural formula for the heme, which are these red flower-looking things. In the center is where we find an atom of iron. So hemoglobin is defined as a pigment that bonds to oxygen and carbon dioxide. Hemoglobin is also a blood test that is run. They check hemoglobin levels to see if the body is able to transport oxygen and carbon dioxide or not. Heme with the iron ion is the pigment that bonds to oxygen. Without iron, you're not going to transport oxygen. And so that's why one type of anemia is called iron deficiency anemia. This is recycled by the liver and the spleen to release bile pigments, which include biliverdin and bilirubin, bile salts, which are also called bile acids, and iron. We want to reuse those. We use bile salts or acids to make bile in order to emulsify lipids. We use the biopigments to add color and attributes to different substances. The biliverdin is prominent in bile, which is why it's green. The bilirubin is orangish yellow. And you can see these pigments when you watch the healing of a bruise. It goes from the purple to the green to the yellow. The green is the biliverdin that's been broken down, and then you get the bilirubin. Globin are the 4 protein strands. So you have 2 yellow ones and 2 blue ones. They are what bonds to carbon dioxide. They are recycled so that we can reuse the amino acids to make other proteins. Here you see a breakdown. Here we go. So nutrients absorbed from eating, triggering hemopoiesis, erythropoiesis in the bone marrow. Erythrocytes circulate for about 120 days. And that used to be the guidelines for donating blood. When they die off, the spleen and the liver are going to recycle them. So we break it into heme and globin, biliverdin, bilirubin produced. We recycle the iron, and if we could see behind this, you would see the bile salts as well. We reuse the amino acids in the globin portion. Blood types. You have the term agglutinogen, which we mentioned back in the lymphatic chapter. These are molecules attached to the erythrocyte, and you can see them. See it here. It's simply a chain of monosaccharides. There are different kinds. Sorry, I marked the wrong thing. So, part of the glycocalyx. So, this carbohydrate and this carbohydrate represent the agglutinogen. Now, we're not going to respond to our agglutinogens. We're going to respond to others. So, it's considered an antigen, not that we respond to ours, but if our blood got given to someone else, they could respond to it. Agglutinins are the antibodies that we produce within plasma, and they bond to certain agglutinogens. The little green satellite-looking things that we see here are the agglutinins. And what you see happening here is the attachment of the antibody to this erythrocyte and this erythrocyte. So it hooks the erythrocytes together. That process is called agglutination, where the antibodies are going to stick the erythrocytes together. So different pieces extending, and what happens is you get a clump that can block blood flow. And it means it's a clump. This is not a clot. In a clot, you're going to see proteins and platelets. In a clump of erythrocytes, you're going to see the agglutinins or antibodies and the agglutinated erythrocytes. So this is what happens when you get the wrong blood type. Blood types are identified compounds within blood. So it's a way of chemically analyzing blood. Some of these compounds are attached to erythrocytes, like we see with the agglutinogens here. Others are floating around in the plasma. We have over 100 different types of blood in humans. In other organisms, they have different numbers. Some of these are genetically controlled, and some of these are environmentally induced. And it has to do with the types of things we've been exposed to and what we develop in order to deal with those. So this is going to be the end of part A. If I can get things.